this. And first thing I want to do is, you'll have a copy of the practice test. It turns out I printed an old version. That's okay. I'll just show you. I posted it on Moodle. Oh, don't need this. So what I'm going to do is I'll just pull it down. So it's in week 5. I posted the practice test. So I have printed copies for anyone who's coming on Thursday and doesn't have one. Okay. But what I'm going to do is I'm just going to open this up and show you the changes that I want to make. Oh, maybe I did the wrong thing. Where did it go? Gotta wonder. I think I was too trigger happy. Create new note. Oh, no, business math. Yeah, whatever. There. So what I want to do, or I want you to do for the practice test, so we'll go through this, at least the long answer questions together in class on Thursday to review for the test that's on Tuesday, right? And so we've got our first test coming up, and so the class before, I like to do a review class, and then you'll have seen it, and we can kind of talk through some things to keep an eye out for, right? And then, but what I find is that if you've tried it, at least before we go through it, then maybe you'll have some idea of, oh, I actually found this question really hard. Because a lot of the time when I'm going through and you guys are sitting there and you're like, yeah, that seems reasonable enough, right? I could probably arrive at that, right? And so what I want you to do is just try all these questions, right? And then scan your answers and post them on Moodle. And that's open until the beginning of class next day. And then as long as you've shown something, it doesn't have to be right, it doesn't have to be complete, just give me something to look at, right? Your attempt at the practice test, I'll give you 1 completion mark as an assignment, right? So it'll be easy marks. You'd be surprised at how many people don't do it, but don't be that person, okay? So easy marks, it doesn't have to be right, just try whatever you can do and then scan it and upload it. So here at the top, it says complete all practice test problems before the review class for test 1. That's still true, but instead of me going around checking your work, upload your scanned work on Moodle before 3 o'clock, sorry, 15 o'clock, 3 o'clock on Thursday, October 3rd. Okay, and there's a little Dropbox there in Moodle, right? Practice test number 1, that's where you're gonna hand it in. Okay? And then I just flip through it and just see how much you did, where you're at, right? I know time is an issue too, so I just want to push you to try this before we go through and do it. Okay? I guess assignment 3 due tonight? All right, make sure you do that. So for today, do practice test number 1 for Thursday. See handout / Moodle, I'll say, for instructions. And also assignment number 3 is due tonight. Eek. So let's do a little bit of review. Okay. Recording app. So last day, right, we went through 3.3, which is where we develop profit functions, right? And then we learn to work with profit functions, and we talk about things like the break-even point, the shutdown point, and just some other terms like that. So given information, we found formulas for the total revenue and total cost. And we're also able to construct profit functions. Construct profit functions. So remember, we started with the profit of X is the total revenue minus the total cost. And then we went through kind of around the formula sheet, right, in that CVP analysis section. Oh, and I'll show you here while I'm on the rampage. On Moodle, I posted at the top, I posted your formula sheet here. So I forgot to bring the extra printouts today, but I'll bring them on Thursday. And then of course, that's the one that you'll have for the test as well. I'll give you clean ones as all. Okay. How about I bring this one in too? So what we said was, okay, we work around, so to build a profit function, we're in the CVP analysis section. We just kind of piece together all those pieces. And so we said, well, total revenue we can replace with P times X minus the total cost we can swap out with the variable cost plus the fixed cost. To get rid of those brackets, we have to mind that negative, right? And so we've got the P of X, PX times, minus the variable cost minus the fixed cost. The variable cost we can swap out with capital C times X, which is the cost to produce each unit, times however many units we have, right? So we get PX minus CX minus the fixed cost. Collecting like terms, we can rewrite this as X times P minus C minus the fixed cost. And then if I give you P, C, and the fixed costs, right, or you're able to pull those together, then you can develop a profit function. We also said, we talked about the shutdown point. The shutdown point is when P is less than C, right? We have to shut it down if the price that we're able to charge per thing is actually less than what it costs to make that thing, right? Which kind of, it makes sense. We also talked about the break-even output, which is when we solve for x, when profit of x is set to 0. Right, so the break-even point is where we go from making a negative profit to making a positive profit. So we force that profit to be 0, and then we solve for x. So what x makes that happen? Any questions about that from last day? No? All right. So what we're going to do, we didn't get into section 3.1 because, like I said, we don't need it until we do monopolies in 3.4. And so I'm just going to get through section 3.1, which is a brief introduction to calculus, but only what we need and then no more, right? So if you've taken calculus before, then great, you're laughing, but if not, don't worry. Who has taken calculus in here? Yeah? So sit back, relax, enjoy the ride. All right. So we will go through section 3.1 before we can do section 3.4, which is really on the docket for today. Okay. So 3.1, is called the basics. I find in this textbook, the first section of all the chapters basically is called the basics. So it's not that helpful, but it's an introduction to calculus. Okay. So we're going to cover just the basics of derivatives, and we'll talk about what derivatives are. Okay. Just the very basics of derivatives. We're not going to talk about definitions. We're not going to talk about theorems. There's obviously a lot more to this than what I'm giving you, right? But we just need to be able to find a derivative, and that's it. Okay. So we will cover the basics of derivatives, but no formal definitions or theorems. Sorry, I will say here though, right, you can look in the textbook for some of the theory. It doesn't even go very deep, right? And so see textbook for some of the theory if interested. That's not a hint or anything. I'm just saying we're not doing it for a reason. Okay. So like we said, we're going to cover some basics of derivatives. Okay. And so let's talk about what a derivative is. The derivative of a function, so we have a function, say the profit function. The derivative of a function gives us a function to find the slope at any point on that function, on the original function. Okay? So it's basically a way to figure out the slope at any point. Okay? Which is helpful, right? Because if we know the slope, right, remember, of a straight line, then we know how quickly things are changing. Okay? And so the derivative of a function let's call that function f of x. Is the slope of the tangent line at any value of x. Oh, yeah, it's for Thursday. Don't worry. So, test 1 is on Tuesday. Review on Thursday. Yeah. Okay, so basically what it gives us a function for finding the slope of the tangent line at any point. Okay. What is the tangent line? The tangent line, you might have heard about, right? The tangent line is the line that touches one point on a graph. Right? So the tangent line is the straight line that only touches a single point on a curve. Straight line that only touches a single point on a curve. So imagine something like this. If you've got your x and your y-axis here, imagine you have a function that looks like this. Here is f of x. And we want to know what the slope is here. So at this point, x equal to a, just any point a, if we draw a straight line now, let me see if I can make sort of a straight line along here. So it's a straight line that only touches the curve at that one point. Yeah. So this here is the tangent line at x equals a. A straight line like that, we know has the form y equals mx plus b, and we can find the slope. And if we have a large slope, right, then we know it's really steep and things are changing really quickly, right? If it's a small slope, then we know that things are just gradually increasing. And even as you move along here, right, move along this curve taking different values of x, right, then here it's increasing really quickly, and then here it's kind of slowing down until at the top, the slope is 0, right? Because if you've got something like this, rise over run, there is no rise. Right, so you've got a slope of 0 here at the maximum, and we're going to use that fact later on. Right? And then we've got a negative slope, and here it's just plummeting. Right? And so knowing how the slope behaves at every point, right, that's going to be helpful. But at the end of the day, we only need it because this is what a profit function looks like for a monopoly. Okay? talk about later. But to maximize that profit function, we find the derivative, which is the slope of the tangent line, force it to be 0, but I'm getting ahead of myself. Okay. For now, we're just talking about derivatives. Bless you. So what we'll find is that each value of x, has its own tangent line. And just to recap what we just said, so the slope of the tangent line, which is the derivative, tells us the rate of change at each value of x. Tells us the rate of change at each, or I'll say slash any value of x. Therefore, now this is just a recap. The derivative of f of x at x equals a is the slope of the tangent line of f of x at x equals a. Okay? So we've said that about 3 times before, but just getting it out there again. Right? So therefore, the derivative of f of x, at x equals a, right? So any point x equals a is the slope of the tangent line of f of x at x equals a. Any questions so far? We haven't really gotten into it. So far, just talking definitions, but. So we need some way to, some notation to denote a derivative. And so we denote the derivative of f of x by f prime of x. Okay, so it's just f and then a little kind of apostrophe f prime of x, which you're going to read f prime of x. Or in our case, we're going to be taking the profit prime of x, which is the derivative of a profit function. in this course, we only need to be able to find the derivative of a polynomial, right? So a polynomial is anything where you have, usually we only go to the power of 2, right? Ax squared plus bx plus c, right? But we'll talk about the general polynomial and how do we take the derivative of it. And so there's rules for all kinds of different functions, right? If you've got, quotient, you have to use the quotient rule, but we're not going to get into any of that. We're only taking derivatives of polynomials. So in this course, we only need to be able to find the derivative of a polynomial. A polynomial has the form. Now this, I usually lose people here, but this is the general form, and then I'll show you what it looks like with numbers in there, and it won't be so bad, right? But a polynomial has the form, let's call it P of x, is a subscript n, x to the power of n, plus a subscript n minus 1 times x to the n minus 1, plus all the way down to a subscript 1, x to the power of 1, plus a subscript 0, x to the power of 0. Blah. If you're feeling lost, it's okay. Like I said, this is where I usually lose people, and now you have to come back. Which one? This one? A subscript 0, x subscript 0, right? We're just making room for n terms, so it can have 1,000 terms. And then, so the nth coefficient has the power of n, right? But here, what we'll actually be seeing, you'll never see something like this, right? We just need it to be able to show that here's how it works in general, okay? But how it actually looks is maybe f of x is 3x to the 4 plus 6x to the 3 plus x squared plus 3. That looks better, right? We've seen things like that maybe, right? Or at least it looks manageable, right? Here, x to the power of 4 is my highest power, right? I've got a power of 4, I've got a power of 3, I've got a power of 2, got a power of nothing. Okay. And so here, my n is 4. So a subscript n in this case is 3. Right? It's just saying you're going to have a coefficient times x to the power of something, a coefficient times x to the power of another thing, one less than the first thing, right? And then it just goes through, and so here we've got x to the power of 3, x to the power of 2. What happened to x to the power of 1? Coefficient must be 0. That can happen, right? It's still a polynomial. Okay? And so polynomials look like this. They look like this. I can't say they don't, but we never see them like that, right? This is the. Okay? So we're going to learn how to take, or how to find the derivative of something that looks like this. Okay? Let's talk about some facts first, just for the actual polynomial. The first fact is that all the a's, right, a subscript n, a subscript n minus 1, a subscript n minus 2, blah, 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 blah. They're all just placeholders for some coefficient. Okay? So all the a's are placeholders for coefficients. Second thing, as a fact, is that anything to the power of 0 0 is 1. So x to the power of 0 is 1. And then our third fact is that x to the power of 1 is x. Or I guess I should write anything to the power of 1. I should have written that first. Anything to the power of 1 is itself. So those are facts. And coefficients are allowed to be 0, right? That's a number, right? Which makes that term go away, right? So even something like f of x is x squared is it's technically a monomial because there's only one term, right? But it's still a polynomial. So we can have something as simple as that and something as nasty as up high, right? That one. Okay. So let's see here. If, and I'm going to rewrite, this is the same p of x that we had earlier, so you don't have to write it in, but I just want to have them to compare them to, right? So write first p of x, the general polynomial, and then below it, I'll write p prime of x, right? The derivative of the polynomial. So if p of x has the form a subscript n, x to the power of n plus a subscript n minus 1, x to the n minus 1, adding through to a subscript 1. I'm not going to write x to the power of 1 this time. Okay. Or I guess I can. Usually I don't. Right, x to the power of 1, what we said in those facts was x to the power of 1 is just x. So usually I just drop it. Right. Plus a to the power of 0, x to the power of 0. And usually I would just write a to the power of 0 because x to the power of 0 is just 1. Right. So if that's p of x, the derivative, the derivative of p of x is going to be p prime of x. So far, so good, right? We've already said, okay, if I have to take the derivative of something, then I just denote it with a little prime here, bless you. And so, like I said, there's rules and there's theorems and there's definitions that we could go through. But what I do to find the derivative is I just imagine you're going to give it a bump from the right-hand side. I know, very technical. You give it a bump, and then what happens is that all these powers go down in front and multiply the coefficient that's there. So all of these, when you give it a bump, all these fall down and multiply your coefficients, and then the powers decrease by 1. So once you take the derivative, then all your powers are going to decrease by 1. So what does it look like? If we were to write this out, I'd have my first coefficient, but then if I give it a bump from the right-hand side, right, and like I said, if you don't like this definition, then of course you can go and read the textbook and it'll give you the formal definitions, but for our purposes, this is going to work just fine. So give it a bump from the right, and then you get a subscript n, whatever it is, times n, that's the old sub or power, times x to the power of n minus 1, right? Because it bumped in front, so it has to decrease by 1, and that's just how derivatives behave, or at least for polynomials, plus a subscript n minus 1, same idea, times n minus 1 times x to the n minus 2 now, right? Or if we want to be particular, n minus 1 minus 1, plus, and then I have to write it on the next line because it gets a little wider now, right? That I have to write all those coefficients in front. A to the power of 1 times x to the power of 1 minus 1 plus a to the power of 0 times 0 times x to the power of 0 minus 1. And like I said, again, don't worry. This is just to go back on if you're not seeing the pattern, right? But once we do an example, I think you'll be fine. Okay. Let's talk about some facts first, though. So some facts about the derivative now. The first one, the derivative of a subscript 1 to the x, the derivative of a subscript 1x, sorry, not to the x, is a subscript 1 times x to the power of 1 minus 1, which is just a subscript 1 times x to the 0, which is just, well, I'll overdo it here, a subscript 1 times 1, and then using that fact that anything to the power of 0 is 1. Okay. If you have any term with just an x and no power, right, or a power of 1, it just becomes the coefficient when you take the derivative, right? And so instead of going through and doing that, we can just remember that if we have a term with just an x, right? So in brackets, I'll put no power. The derivative is just the coefficient. Oops. Keeps glitching out here. I guess I'll rewrite it. is just the coefficient. And then the second fact that we're going to use, you'll notice that these are just having to do with the tail end, right, where we have just a single x and then just a constant value. Okay. If you think about the graph of a constant value, right, y equals 4, for example, you have just a straight line. And then if you think about the slope at any point, that's just going to be 0. So it makes sense that the derivative is just going to be 0, right? The derivative of a subscript 0 times x to the power of 0, right? Or just a subscript 0, right? Because usually we don't write x to the power of 0, or a subscript 0, is a subscript 0 times x to the 0 minus 1, which is just going to be something times 0 times x to the negative 1, but everything times 0 is just going to go to 0, which is just 0. So therefore, the derivative of a constant is 0. Okay. Here, I'm going to write out my my method for finding the derivative of a polynomial, right, where I give it a bump and things fall down. Then we'll do an example, and I think things will fall into place. I will preface it with, there are technical ways of doing things, right, but we're not going to use them. Okay, so there are technical ways, of course, just so you don't, I don't think anyone's thinking that there aren't. So there are technical ways of finding the derivative of a polynomial. The derivative of a polynomial but I imagine giving my function a bump from the right. So, but I imagine giving my function a bump from the right making the powers fall down then I'll put in brackets to multiply with the existing coefficient. To multiply with the existing coefficient and decreasing the powers by 1. That's wordy and whatever. So let's see if we can have a look at an actual example. So example, if again we let f of x be let's use that 3x to the power of 4 plus 6x to the 3 plus x squared plus 3, right? That's a polynomial. Find f prime of x, right? Find the derivative of f of x. F prime of x is going to be, so here, right, way more reasonable. Imagine you're just going to give it a good shove, and what happens is that this 4 falls down in front and multiplies by the 3, and in doing so, you have to decrease this by 1, so 4 becomes 3. Same thing here, this 3 falls down in front and it decreases to 2. This 2 falls down in front and it decreases to 1. The derivative of a constant goes away, it's 0. Right? So what we have is we get 3 times 4 times x to the power of 4 minus 1. And if you went straight to 3, that's fine. Right? If you went straight to writing 12 times x to the power of 3 there, that's fine. I'm just showing all the steps. Okay? Plus 6 times 3 times x to the 3 minus 1. Plus, technically, so, bless you, x squared has a coefficient of 1, right? There's just an invisible 1 out front there, right? And so what we have is just 1 times 2 times x to the power of 2 minus 1 plus 0, right? Reason being, you could write that constant 3 as 3x to the power of 0, right? And then you'll see why that term goes to 0, right? Because when you bump that 0 down in front, everything's being multiplied by 0 and it disappears. Right? So if you like to have that there, then fine. But I usually just drop it to 0. Okay. So if we simplify this, right, 3 times 4 is 12, times x to the power of 4 minus 1 is 3, plus 6 times 3 is 18, x to the power of 3 minus 1 is 2, plus 1 times 2 is 2 times x to the power of 2 minus 1 is 1. Right. Plus 0. And if we want to simplify this even more, right, I'm not going to write the x to the power of 1 and the 0. Right? And so, or we can write 12x to the power of 3 plus 18x squared plus 2x. So whenever we take the derivative, it becomes a smaller, lower power function, right? It's still a function, but it just, instead of a power of 4, it's a power of 3, right? The highest power. So when we're talking about polynomials, just so you're not confused if you're reading things, if the highest power is x to the power of 4, we call it a polynomial degree 4. Here, once you take the derivative, you get a polynomial degree 3. That's just a little terminology in case you're reading a problem and you're like, degree 4, how do I know? Okay. So here, f of x is a polynomial degree 4, and f prime of x is still a polynomial, but it's degree 3. So it is a polynomial degree 3. Third degree, fourth degree, doesn't matter. Okay. Remember that the reason that we were finding the derivatives point x equals a. So what we do is once we have the general derivative, then we plug in x equals a. Let's say I want to find the slope at x equals 2, right? Then we plug in x equals 2 into the derivative, and that's the slope at x equals 2. Okay? And so f prime of x is the function for finding the slope of the tangent line of f of x at x equals a by calculating f prime at a. Okay. So for example, if I asked you to find what is the slope of the tangent line of, do you want a different function or use the same function we just found the derivative of? It's all the same. Anyways, let's just use the one that we just did. F of x is 3x to the 4 plus 6x to the 3 plus x squared plus 3 at x equals 2. We know that f prime of x, we just found it, is 12x to the 3, oops, it's a nasty 3, 12x to the 3 plus 18x squared plus 2x. And so we need to find f prime at 2. F prime at 2 is 12 times 2 to the power of 3 plus 18 times 2 squared plus 2 times 2, right? We're just, wherever we see an x, we're going to substitute 2. So this becomes 12 times 8 plus 18 times 4 plus 2 times 2 is 4. We get 96 plus 72 plus 4. So the slope of f of x at x equals 2 is 172. Yeah, you bet. Is that okay? So we're going to be talking about monopolies, right? But a lot of profit functions kind of look like this upside down parabola, right? And so that's why we're having to find derivatives, because those parabolas are polynomials, and so we need to be able to deal with those specifically. Okay. But if we write, so in a monopoly, and we'll talk more about monopolies specifically, but here we'll just introduce it. So in a monopoly, the profit function looks like this. So we've got, and we've seen this once before, right, when I was trying to explain. So we've got the x-axis, we've got the profit of x on the y-axis, and then we've got this upside down parabola. If these are the profits, right, increasing here, I think if I asked you, hey, if these are your possible profits, which one do you want? Oh, I want this one, really, right? And so we need to be able to find, okay, well, how do we find the value of x that forces us to be up here yet? Oh, just stretch. It's allowed. I'm just on the lookout. Okay, and so what we're going to be doing is we're going to say, okay, well, of course I want to have this profit, right? So I need to know, okay, well, what x is going to make that happen, right? And what is my profit going to be at that point, right? So what we said earlier was we use the fact that at this very point, that very peak, that's the only point where the slope is 0, right? So if you draw a tangent line at that point, the slope is 0. Okay. So let's start there. So let's say here, at this point, this is the maximized profit. And then if I draw a tangent line, it's a bit of a downward slope. Imagine it's completely straight, or completely horizontal, rather. The slope of the tangent line is 0. Okay. Don't worry, I'm going to write that as a fact. Fact. The slope of the tangent line but really, we could replace the slope of the tangent line with just the derivative. At any peak or valley, right, any maximum or minimum, so any peak or valley, right, we're only going to be dealing with peaks, right? Maximize the profit, that's our goal here. But it works for the minimum too, right? What's your minimum profit if you've got an upside down? That's not good, right? it wouldn't look like that, but. So at any peak or valley of a function, will be 0. Okay. So to maximize a function, what we do is we're going to follow some steps here. To maximize a function, first thing you're going to do is find the derivative of that function. Find the derivative. Once you have your derivative, right, the derivative is the slope of the tangent line at any point of x, right? What we want is we want to find the point of x that makes the derivative 0, right? So what we do is we set the derivative equal to 0. Okay. Set the derivative equal to 0. Solve for x. Right. Next thing we do is, okay, now we forced our derivative to be 0. What value of x makes that happen? Right. So solve for x, which in other terms, find the value of x. Find the value of x that makes the derivative 0, right? That's the same thing. Fourth thing is not really even a step, right? This is the x that will maximize your function. That will maximize your function. Usually, right, we're talking about how many things do I need to sell in order to make this much in profit, right? And so usually we're talking about, okay, X is the output, right? How many things do I have to sell or get rid of here in order to maximize my profit? Okay. Another step that you might want to take, right, if I ask you to evaluate the original function at that point of x, because the original function is the one that tells you what your profit is, right? So that's essentially finding the profit at the maximized point, right? So finding our maximized profit. So use x in the original function to find the maximized value example 77. Maximize f of x is negative 5x squared plus 250x minus 500. Okay. And if you have a look on the practice test, that looks a lot like question 2. Looks like question 1 too, right? But question 1 is different. We're always maximizing our profit one way or another, right? Or we're trying to, right? Question 1 is that linear programming. Question 2 is what we're doing now. Okay? So it could be as simple as this: maximize this function. Okay? And that just means that we're going to go through and do all these steps 1 through 5. Okay? So the first thing we're going to do is find the derivative. Find the derivative. F prime of x is -5 times 2x to the power of 1. Oh, excuse me. Which, yeah, I'll write it. You don't have to. Plus 250 times 1 times x to the 1 minus, 1 minus 0. Right, the derivative of a constant just goes away. So we have the derivative is -10x plus 250. So see how your derivative is always smaller than the original function, right? Whether it be the number of terms, right? If there's a constant, you'll have less terms, or if it's just the power, right? We started with degree 2, and then we went to degree 1. Right? So, first step, find the derivative. Done. Second step, let f prime of x equals 0. That's just shorthand for that second step, right? Set the derivative equal to 0. That's the same as saying f prime of x equals 0. Right? So then we're saying, okay, well, 0 must be -10x plus 250. Step 3, solve for x, right? So if 0 is -10x plus 250, solving for x isn't that bad, right? Because we're gonna I'll move my -10x over to the left-hand side, because then I'll be rid of that negative, right? And so I'll have 10x is 250. Solving for x, I've got 250 divided by 10, so x is 25. Okay. If we're thinking about this kind of curve, right? This curve was f of x is -5x squared plus 250x minus 500. What we found is that, okay, at this point, x is 25, right? But if we want to maximize f of x, right, if we want to maximize f of x, we need to find the f of x at x equals 25, right? So what we do is we just plug in x equals 25, and that's the maximized value of f of x. So what step was that? 4 now. step 4, I guess, and step 5. They're not really real steps in my list, I guess. I'll have to clean it up a bit, but that's all right. Find f of x at the x found in step 3, right? So now just remember that you have to go back to that original function, and we're going to find f of 25 is negative 5 times 25 squared plus 250 times 25, and then minus 500. This becomes negative 3,125 plus 6,250 minus 500, 2,625. Therefore, f of x is maximized to 2625 at x equals 25. So that's about a 10-mark question, right? But as long as you remember those steps, then it's not that bad, right? And remember how to take the derivative, or at least for us, the derivative of a polynomial, then you'll be okay. Any questions about derivatives before we get into monopolies specifically? Yeah, step 4, I kind of smushed with step 5 because my step 4 wasn't really a step. It just said, this is the x that will maximize your function. And then step 5 is use x in the original function to find the maximized value. Right, so I just kind of smushed them together. So there's, as far as the steps go, there's only 4 real steps. Okay. 3.4 is on monopoly. A monopoly is when we have many buyers and a single, or, well, a single typically, but or very, very few sellers, right? So they have a monopoly. So many buyers, oops. And only a single seller. Skip this page break here. And recall, so I can do a nice big graph. That if we have something like this, right, where we've got the profit of x on the y-axis and x on the x-axis, and we've got some profit function here, then at this point, This is our maximized profit. It's maximized at some point x equals a, let's say. And at this point, the derivative is 0. So I can give you a profit function, right, and say maximize this thing, right? Or I could give you the total revenue and the total cost, and you can build your profit function just like we did last day, right, where we built our profit function. And so given the total revenue and total cost, we can develop the profit function. Yeah, sorry. More? Oh, it's my page break. So we can develop the profit function and say, well, profit of x, just the same way we did last day, is the total revenue minus the total cost. That's still true. And these are going to be the same steps, right? But now in terms of the profit, so if we want to maximize profit, if we want to maximize the profit, your first step is to find the derivative of the profit. So find profit prime of x. I guess I should write find. Not very helpful if I just say profit prime. Oops, I almost did it again. Find profit prime of x. Let the profit prime of x, right, let the derivative be 0. Solve for x. X is the maximized output, right? So it's not the maximized profit, but it is the maximized output. Let's say for the next step, say x equals a. X is going to be some number. Before it was 25, right? So a would be 25, right? So I'm just using a as a placeholder. Step 4 is find the profit at a. Use original profit function. Right? Not the derivative anymore. Profit of A is the maximized profit. I'm just going to steal example 112, but we'll just write it out. Suppose total revenue is 100x minus x squared, and the total cost is 40x. What is the profit maximizing level of output and what is the maximized profit? What is the maximized profit? All right. So essentially it's asking what's X and what's the profit at that point of X. So step one, or part A, what is the profit maximizing level of output? Well, we can find our profit function, our profit of X, even if we only know the total revenues and minus the total cost, we can do that, right? That's always going to be true. And then we can substitute what we do know, the total revenue, we can replace it with 100x minus x squared. And then minus the total cost, which is 40x.
It was 100? It's 10.
Let's change it to 100. Otherwise, our numbers aren't going to work out. That's my bad. 100. 100x minus x squared, 40x. The rest I'm standing by. Right, so the total revenue is 100x minus x squared, not 10x minus x squared. Good, thank you. That would have been disastrous. So we can ditch these brackets. They're not doing anything, right? We're not multiplying by negative, so we don't have to be careful. We've got 100x minus x squared minus 40x. Now, I like to write all my higher power. I like to have my powers decreasing, right? So first thing I'm going to do is I'm going to swap this around and say minus x squared. And then 100x minus 40x, I can just rewrite as plus 60x, right, if I collect like terms. So this is my profit function. If I let 0 equal my profit function. Oh, sorry. Haha, skipped a step. We have to find the derivative first. Right. The profit prime of x. Oh. Profit prime of x is going to be, we bump these powers down, right? So we get negative 2x plus 60. Now we're going to let that be 0. So let 0 be the profit prime of x is negative 2x plus 60. And solve for x. So if we have 0 is negative 2x plus 60, right, solving for x, I'm going to move that negative 2x over, so I get 2x is 60, so x must be 30. $60 divided by 2 is 30. So the profit is maximized at x equals 30. Right. So therefore, the profit maximizing level of output is x equals 30. And then part B asks, find the maximized profit well, that's just taking the profit of x evaluated at 30. And the profit function we said was negative x squared plus 60x, negative 30 squared plus 60 times 30. Paying attention that you're using the original profit function, which is going to be, so 30 squared is 900, so we get negative 900 plus 60 times 30 is 1,800. So we get positive 900. Therefore, the maximized profit is 900. Right. We don't really have units. It could be 900,000. It could be 900 million, or just $900. Who knows, right? But it's not important. So you can take a total revenue and a total cost. You can develop the profit function, and then you can take the derivative of it, set it to 0, solve for x. That's your maximizing output, and then use that x in your profit function to find the maximized profit. Okay. And on your practice test, right, that's question 4, right? Something similar. Okay. So we did talk about 2 different questions on test 1 today, right? So it was a big day, but they are doing the same thing, right? Maximizing some polynomial. Yeah. Yeah. It's outside the brackets, yeah. And that's important, right? So it's only the 30 that's squared, not negative 30, because then we'd have a positive, right? So we have to keep that negative outside, right? Because it's negative x squared. So you're just squaring the x. Yeah, good. Any other questions? No? All right. So if you didn't get a practice test at the beginning of class, you can come grab one here. We'll go through it on Thursday. Otherwise, I'll stick around if you have questions, but otherwise we're done. You did it, guys. It's a lot of writing. Of course. I'll bring this back up, but I just want to end this recording.